Alright, continuing off to the 2023 variants. Here we go. Let's switch to the color red. Okay, 2023, the weather is good, summer, and paper 5 1. Question number 2. Find the number of ways in which a committee of 6 people, okay, committee of 6 people, can be chosen. I know it's already a combination question. From 6 men and 8 women, if it must include 3 men and 3 women. Okay, simple question. A committee of 6 members, 6 people I need to select. Out of them, three must be men members. Let me write that down. 3 members, 6 members की committee बनानी है. Out of them, 3 must be men and 3 must be women, right? So how do we do that? Simple. Simply just out of the 6 men you have available, select 3. The committee is still not complete, so we multiply. And out of the 8 women we have, any 3 can appear in the team. And that is your committee formed. Easy. Let me get you the answer. What is the answer? 6c3 into 8c3. 1120. There we go. 1120 ways. Acha. Part B. A different committee of 6 people. Another committee we need to form, I guess, of 6 people again from the same selections. 3 of the 6 men are brothers. Okay. Now we are making a distinction, which is that out of these 6 men, 3 are brothers, and while the rest are just normal people. That's a distinction, right? So we always make a distinction. Part B now states, find the number of ways in which the committee can be chosen. Combination. If there are no restrictions on the number of men and women, okay, but it must include no more than 2 of the brothers. Interesting, very interesting question. Let's think about it. Firstly, okay, 6 people की committee बनानी है, ठीक है? So 1, 2, 3, 4, 5, 6, got it. It must include no more than 2 of the brothers. That means no more than 2, right? No more than 2 means the brothers cannot be greater than 2. Understood? Which means they can be 0 in quantity, there can be 1, there can be 2 of the brothers, but there cannot be or they cannot all 3 be in the committee, right? There could be none of them, there could be 1 of them, there could be 2 of them, because no more refers to greater, not greater than equal to. It refers to greater, right? So no more than 2, that means greater than 2. No more than 2 refers to greater than 2. That means 2 brothers can be part of the committee. In another case, 1 of them can only be part of the committee. And 0 is also something to consider. I have repeated myself multiple times, and maybe it's possible none of the brothers are part of the committee. So let's do that. 3 cases we need to form. Firstly, uh, 3 men remaining plus your remaining women, which you had were 8. 8 women. So this whole thing will add up to 3 plus 8 is 11 people. 11 total people, and this is your brothers. 3 brothers. I'm just gonna circle that. Okay. So first case is 0 brothers. 0 brothers. That would mean that out of the 11 remaining people in which the brothers are not part, right? The brothers are not in these 11 people. Random men and women are in this group of people. Out of them, any 6 will be selected and put in a team, and the committee is formed. 1 case done. Now I just want to include 1 brother. Out of the 3, any one can be part of the team, no more than 1, right? So let's make sure any one of the brothers, that means, actually wait, in which this committee, there are no section, okay. Like I've said, now this is a funny thing. Let me think about it. Give me a second. Should we fix the brother that should be part of the committee? Or should we select him out of these 3? That is the tricky part. Well, I think we should select them. You know why? Because I know there are 3 brothers, but within these brothers, there's no certain distinction. Okay, one is Yasir, one is Ahmed, and one is Muhammad, right? Common names. Maybe not, I don't know. But if there was a distinction like that, and that 1 brother had to be Muhammad or that 1 brother had to be Yasir, I would have known, okay, I need to fix them, right? But here it's a very open open-minded situation where they've just referred to brothers, right? So I will go for a selection. I will say out of the three brothers, anyone can be part of the committee, and for the remaining five positions, out of the 11 people in which the brothers are not part, any five can be part of the team, right? So 1 plus 5 is 6. The committee is formed. The next case is of two brothers. Two brothers two can be part of the committee. Any two. So out of the three, any two can be part of the committee. Moving on. Now out of the remaining 11 people, any four can be part of the committee. So 2 plus 4 is 6. The committee is formed. And let's add them up. 11C, 11C6 plus 3C1, 3C1 into 11C5 plus 3C2 into 11C4. Nice. So the answer we're getting is 2838 ways of selection. And that, my friends, is your answer. So make sure your thought process is within line. That's it. This is a very good question. I wanted more parts, but oh well. Part 3. Okay. 3A. Find the number of different arrangements of the 8 letters in the word cocoon. Okay, easy 8 factorial. Arranging all of the letters, move back and forth to give you a different arrangement. Divide by anything that repeats. What does repeat? C's I'm seeing repeated twice. Divide by 2 factorial to remove them. O repeats 1, 2, 3. So divide by 3 factorial as well. And that would be about it. Yep, get the answer. 8 factorial divided by 2 factorial into 3 factorial. That is 3360 ways. Okay, moving on. Part B. Find the number of different arrangements of the 8 letters in the word cocoon. Okay, I know it's factorial because I'm arranging all the 8 letters. So all my positions are being filled and I'm left empty-handed, right? So that means it's a factorial question. In the word cocoon, in which the first letter is O and the last letter is N. Simple question. The first letter has to be O. So that's going to be fixed. The last letter has to be N. So it will also be fixed. Forget about these two positions. Now let's play in between. 8 minus 2 is 6. So 1, 2, 3, 4, 5, 6 positions remain, which I'm going to form the different arrangements. Let's do that as well. Now, anything else? No, nothing else. Okay, no other condition. Well, easy question, but 2 marks there. Sahi hai. So 6 factorial, all of them can move about to give a different arrangement each time, divided by the anything that repeats. So 2 O's will be repeating because this O has been used. So I'm not going to think about that anymore. These C's will repeat and these 2 O's will repeat only. So 2 factorial, 2 factorial. Now this is something interesting. Anything that moves will cause a repetition if there are more than one. For example, there are two O's, and in this 6 factorial, I am considering their movement as well, right? Maybe one of the O's is here, another O is here, and it will be moving. While this O is fixed, it is staying, not it is stationary, not moving at all. So I do not need to go for a 3 factorial over here. I'm going to go for a 2 factorial because only two O's will cause a repetition. Make sense? Moving on. Part C. Read up please while I hydrate myself. Okay, find the probability that a randomly chosen arrangement of the 8 letters in the word cocooned has all three O's together, given that the two C's are next. I have done this question, haven't I? In the tricky questions video, I'm guessing. Or maybe the probability video, I don't remember. Probability video, yes, 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 I remember this question. Well, let's get it out of the way again. Favorable conditions first. Favorable conditions. Numerator के लिए working कर रहे हैं पहले. Has all three O's together, given that two C's are next to each other. Now this is an interesting thing. This is a special kind of probability. This is not your normal everyday probability. So that's not how you're going to do it. There's a formula. Whenever the phrase probability and given that are in the same question or part, you will apply the conditional probability formula. I'll give you the formula. The formula goes simple. Probability of any two first scenario, second scenario, this straight line refers to given that, equals to probability of A intersection B. A intersection B means those two events occurring simultaneously, occurring at the same time. Okay, and the next denominator is going to be probability of event B, the event that comes after given that. So this event, which will be your B, probability of B. Got it? So let's give meaning to these letters. Probability of O's being together. So I'm going to refer to O to the power T. Given that the two C's are next to each other. So all C's are next to each other. I'm just going to go with that. Or do I want to save space? I do not actually. I have a lot of space. There we go. So probability of O to the power T, that means all three O's being together. Given Asha, intersection, all C's are next to each other. That also means they actually two C's. Yeah, they're next to each other, bro. That means all C's are together as well. So C to the power T as well, divided by probability of C's being together. Okay, so this is the formula we're gonna use. This is an arrangement question, so probability plus factorial. Let's do it. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Put the O's together. How many O's? 3 O's. There we go. La, 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 la. There we go. And we have C to the power T. C to the power. All C's being together. So I have two C's. 1 and 2. There we go. Boop. And lastly, any other thing to meet? Nothing. So that's your favorable conditions. No. There is another thing that's going to happen here, and you're going to be a little mad because this is going to complicate things for us, but not to worry. Let's think about it. See, this is a conditional probability question, very specific thing to refer to, right? Conditional probability of certain formula we derive it from. Now we are finding a probability here, but even though it is a probability question, we will not consider the inside the box repetitions. We will remove the repetitions itself. Why? Because in the denominator, the repetitions for O to the power T will not be considered, right? And they will never cancel out like they were in all our previous questions. So that is something we will have to consider here. In conditional probability, we do not follow our normal rules of probability. This is just an observation. I'm pretty sure it should be this way, as because it's a probability of O's and O's being together and C's being together, right? It is a probability that I'm trying to find. So I should consider most possible, all possible arrangements. But still, this is not what the examiner requires you to do, and I am bound by the marking scheme. So that is how we're going to do it. Whenever it's a conditional probability question, you're going to do it like a normal person, give the different arrangements. Got it? So we're going to work with different arrangements. So inside this box, it's going to be 3 factorial divided by 3 factorial, cancel out. Same thing for here, denote that as 1. 1, 2, 3, 4, 5. 5 objects moving around, 5 factorial, nothing repeats. That is all that your favorable outcome is going to be, if I am not wrong. Yep. And your denominator has to consider a case when only the C's are together. So let's do that as well. Remove this. Only the C's being together. So only putting the C's together now. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8. So 1, this whole box, 2, 3, 4, 5, 6, 7. So that's going to be 7 factorial. Inside the box is just going to be denoted as 1, right? Because 2 factorial divided by 2 factorial. Because both of these move around to give the same arrangement. And again, if it's a conditional probability question, even though it is a probability plus factorial question, we will still give the different arrangements as our answer. Okay? 1 into 7 factorial into what else? 1 into 7 factorial into did I miss something? Actually, no, that's going to be it. Okay, that's it. There we go. 1 into 7 factorial. Yep, that's it. 5 factorial divided by 7 factorial. Your answer is gonna be 1 over 42. 1 over 42. Answer. Yep, there we go. So this is the formula. This is how you're gonna do it. I hope that made sense. Yep. Eight letters. 1, 2, 3, 4, 5, 6, 7, 8. Just a little checkup. One and then 1, 2, 3, 4, 5, 6, 7. Yep, that makes sense. Everything makes sense and is done, right? So yeah, bound by the marking scheme, unfortunately. I mean, of course, when we're calculating probable arrangements or most possible arrangements, all the possible arrangements, we usually do consider the repetitions and the probability can change. I think it will change, of course, because the arrangements have increased, right? So there will be cases or make questions in the future where I think the probability can change of your selections. But that a question like that has not been tested. And if it's a conditional probability, we just give different arrangement. But if it's a normal, if it is the normal conventional probability, which is your favorable outcomes divided by total outcomes, you will use the logics of all possible arrangements. So keep that in mind. Before we move on, apologies, people. I was missing something here. Before I moved on, I was checking this again and I saw this. See, if I'm fixing the if I'm putting the C's together, I forgot that the O's will be repeating on the outside because they're moving around, right? So let's just move in the 7 factorial out of this. The 3 O's will be repeating, right? So we do need to remove those. That's going to be divided by 3 factorial and your answer is going to change a little. It's going to be, let me do that. 5 factorial divided by 7 factorial divided by 3 factorial. I hope some of you saw that before me. So that would be a proud moment. 1 over 7 is your new answer. Correct answer. Right? Let's move on now. Good thing to always review things, right? Always recheck. That helps always. Even in the exam, I remember doing some stupid mistakes and I was rechecking my paper and I was like, oh shit, I need to do this again. And I was like, 5 minutes remain, I need to fix this again. And you lose marks, right? We do not want to do that. So a good lesson here is to recheck always. To not make mistakes like forgetting to remove the repetitions, right? Because that happened to my friend. He was like, "Hey, Saman, I forgot to remove the arrangements on the Casablanca question," and I'm like, "Dude, तुम्हारा numerator बिल्कुल perfect है, पर तुमने remove नहीं किया repetition, अजीब आदमी हो." होता है. It happens, but you need to make sure it doesn't. Okay, so always review. Moving on. Whether same now variant two. Alrighty. Question 6. Question 6. In a group of 25 people, 6 swimmers, 8 cyclists, 11. Good lord. 6 swimmers, 8 cyclists, 11 runners. Yep. Each person competes in only one of these sports. Okay. A team of 7 people is to be selected. Combination. From these 25 people to take part in a competition, find the number of different ways in which the team of 7 can be selected if it consists of exactly one swimmer, at least 4 cyclists, and at most 2 runners. Got it? Okay, so out of this is your total number of people, and you need to satisfy these 3 conditions. 4 marks. This is a good question. Let's make 3 columns, because why not? I'm going to change colors, make 3 columns. 1, 2, 3. बहुत ज़्यादा बड़े बना दी, wait. 1, 2, 3. There we go. So this is gonna be for your swimmers, this is gonna be for your cyclists, and this is gonna be for your runners. Now, we need to form a team of 7 people total. Okay. So one swimmer has to be in the team always. That's gonna be 1, 1, 1. Let's just fix that. That means I'm selecting 6 people. So these two will always add up to 6. Now, there must at least be 4 cyclists. So let's begin with 4. 4 cyclists. That means greater than equal to 4. And I can go all the way to 8. 4, 5, 6. Not all the way to 8, but makes sense. So if I have 4 cyclists, I can have less than equal to 2 runners. So that is my one case, one basic case. Another could be I could have 5 cyclists and 1 runner at most, right? I could have 6 cyclists but 0 runners. That is a possibility. Adds up to 7, adds up to 7, adds up to 7 each time. Anything else, people? Anything else that would be coming to mind? If I have one swimmer, can I? May I? I don't think so. Let's do the calculation, and if I think of something, I'll add it. Okay, so it's gonna be 6C1 for the swimmers. For the cyclists, it's gonna be 8C4, and lastly for the runners, it's gonna be 11C2. Plus the second case again 6C1 into 8C5 into 11C1. Moving on to the final case 6C1. Oh my god, what is with that 6? It had a seizure. 8C6 and none of the runners. 11C0. I think that would be about it. 142, 151, 160. I cannot decrease this, but I can increase. I can decrease this, not increase this. Yep. No, no, no. No other cases. This is your answer. Ha. 6C1 into 8C4 into 11C2. I think the best way to learn from here would be to listen to my thought process rather than just my words, because that would help you out more. 8C5 into 11C1 plus 6C1 into 8C6 into 11C0. It is a great thing to observe, you know. You can learn way more from just observation rather than listening or looking for lessons in people's words. 26964. Ways of selection. Oh, ways of selection. Answer. 26964 is a good answer. 6 part B. For another competition, a team of 9 people now consists. A team is formed already of 9 people. 2 swimmers हैं उसमें 3 cyclists हैं और 4 runners. Got it? The team members stand in a line for a photograph. Okay. How many different arrangements are there of the 9 people that the swimmers are standing together? The cyclists are standing together and the runners are standing together. Okay. Sorry that I just ate, so I'm feeling a little weird. So how will we attempt this question? I think this is pretty easy. 2 swimmers. So one, two, swimmer, swimmer, box them up. They have to be together. They're standing in a line, right? So how many cyclists? Three. One, two, three. 3 positions, box them up. Anything that you need together, box that shit up. I need to stop saying that word. One, two, three, 4 runners. That they also have to be together. 4 positions occupied. One, two, three, four. Box them up as well. Now they 1, 2, 3, 4, 5, 6, 7, 8, 9. Now all 9 people stand together. That means inside the box. Now keep in mind these swimmers. Now we are donating them as S's and C's and R's. That would fool our mind to think that, oh my God, inside the box is just gonna be one because it will be something like this, right? No, 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 no. No, people, this does not represent an alphabet here. It represents humans. And humans moving around will give you a different arrangement each time. So inside this box, we have 2 factorial. Inside that box, we have 3 factorial. Inside that box, we have 4 factorial. And lastly, we have all these, while being together, all these objects, one, two, three, outside the box, moving as well. So 3 factorial, right? Because the runners can be in this position while all the cyclists can move to that position. Same for all the rest of the cases. That is your answer. So 2 factorial into 3 factorial into 4 factorial into 3 factorial again. 1728 ways of arranging. Can you imagine? Like there are 1728 ways these 9 people could stand and give you a different picture. And the photographer would be like, हाँ भाई ऐसे खड़े हो जाओ picture ले लेते हैं. But there were 1728 ways. This is a very, Doctor Strange. Any Marvel fans out there, please comment. Doctor Strange kind of thing, He's like, okay, maybe he was just running all the combinations and permutations and was like, "Da, da, 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 da. There are 6 billion and only in one we come into the mind of the photographer to stand a certain way, and that picture will be posted on New York Times magazine, right? That is interesting to think about. Part C. Moving on. Read about it, please. 4 marks looks like a good question. Okay, we are still taking a photograph, but this time the cyclists cannot be next to each other. What does that mean, people? Keyword is there. These cyclists are not next to each other ever. That means how many, despite the number of cyclists, how many did we have? Three cyclists. So all three cyclists in any arrangement can never be next to each other. Matlab, they always have to be separated. They always have to have a swimmer or a runner between them. So we will use the universal separation technique. How do we do that? Let's look into this. Um, do we have any other condition? We do not. So okay. So now, how do we go about the universal separation method? Simple. Firstly, forget about the people you need to separate. Cycle, we had three cyclists, forget about them for now. How many others? Two swimmers and four runners. Forget about these people for now and arrange the swimmers and runners. So one, two, three, four, five, six. All six people arranged. Now, let's think about their movement. One, two, three, four, five. Five people can move about to give a different arrangement each time. Now let's unlock positions. How do you unlock positions? We think about the first position, all positions in between, and we think about the last position. How many did we unlock? One, two, three, four, five, six, seven. Seven positions have been unlocked, but only three will be occupied by the cyclists, and they can move about their places. For example, one stands here, one stands here. Or maybe if it is an aspect of one standing here, there, there. All these three will move about their own positions. That's why I'm adding a 3 factorial, turning this whole thing into permutation to give a different arrangement each time. And that, my friends, is your answer. Simple question, 4 marks, free game. 5 factorial into 7c3 into 3 factorial. Anything am I missing anything? I do not think so. So your answer is 25,200 ways of arrangement. Alright people, it happened again. I'm sorry it happened again. I was reviewing the whole thing after I'm done and I'm like, I was like, okay, let's open this question up. I was like, yeah, ये सही तो किया है. But Google पे it was a different answer, right? I was like, what? Why? How is this wrong? And then I was like, one swimmer, two swimmer, three, four, five, six. And what have I written? 5 factorial. Genius, man. This is 6 factorial, not 5 factorial. Please don't make a counting. How did I count that wrong? One, two, three, four, five, six. It's 6. Why is it? Here it happens. Just review. Please always review. Don't make mistakes like these. At least our concepts are good, so that's good. But please, repetition is something you always question yourself. And countings are correct is always something you're going to question yourself for, right? And all the cases you've covered is something you can question yourself for. Those are some things to definitely keep in mind, right? Because those are the three mistakes we've made in the past, and that should be added to the list, right? And we could make a standard list of questions in every question that would help us out, right? So learn, right? Moving on. Variant 3. Casablanca. That word randomly appeared in my mind when I was giving you the example. Casablanca. Here we go. Find the number of different arrangements of the 10 letters in which the two C's are not together. Same thing, universal separation method. That's your keyword. This is still universal separation method. Do this before me, please. 10 factorial. Actually, no. That's not how we do it. What do we need to separate? We need to separate the C's. So let's forget about the C's for 2 seconds. One, two, removed. Arrange the rest of them. We have A, we have S, we have A, we have B, we have L, we have A again, we have N. When we have A again, how many A's do we have? Good Lord. One, two, three, four. Okay. So all these can move about their own position. One, two, three, four, five, six, seven. That's 1, 2, 3, 4, 5, 6, 7, 8. We have 8 people. Oh, sorry, 8 alphabets that can move about their own position. And now the alphabet is only renowned as an alphabet. So 4 A's are repeating. Remove those, right? Moving along, we have 8 factorial divided by 4 factorial. Now we unlock positions. How do we unlock positions? We consider the first position, everything in between, bada bing and bada boom, and the last position. Now, how many did we unlock? 1, 2, 3, 4, 5, 6, 7, 8, 9. We unlocked 9 positions. Out of them, how many will be filled by the C's? Only 2. And into 2 factorial, because whatever C is here, whatever C is here, they move about their own position to give you a different arrangement. But an alphabet is only an alphabet here, right? This is not humans. So they will arrange themselves. This 2 factorial will give the same arrangement. Hence, we divide by 2 factorial to remove those repetitions. And it is just gonna cancel out. Easy question. 8 factorial divided by 4 factorial into 9 C2. अच्छा भाई तो our answer is 60480 ways of arranging. Good stuff. 7 part B. Find the number of different arrangements of the 10 letters in the word Casablanca. Factorial question. I hope you identified that. I do not need to speak it again and again. Which have an A at the beginning and A at the end and exactly 3 letters between the two. C is very simple question. Let's get it over with quickly. Okay, 10 positions. Let's make 10 positions work. First, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A's at each end, 1A here, 1A here. Could be any one of them, doesn't matter. We need to give different arrangements. So we do not need to consider this A being there and this A being there. They are just fine as they are fixed. Anything that is fixed, we forget about, right? So forget about 2 of the 4 A's. Keep that in mind. Do not forget these 2 A's will still cause a repetition just like the O's. We cannot make that mistake again. Learning is the best thing. I love it. Make mistakes, do not get stuck. Learn, move on. Be a goldfish, right? Anyways, so the first condition satisfied. Now this condition. We're only playing along these grounds. So 1, 2, 3, 4, 5, 6, 7, 8. 8 things we need to move. I place a C here, 1, 2, 3, 3 in between, another C could be here, right? Now, same method, letters between letters. Let's just fix these C's here. This C is also fixed. And calculate the arrangements 1, 2, 3, 4, 5, 6. 6 factorial for the remaining arrangement. What does repeat? Now the C's are gone, right? They are unfixed. So forget about them. The A's are moving. Where are the movements I just got? The movement I just counted. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Sorry, 6. So all these 6 movements, the 2 A's are part of it, right? So divide by 2 factorial. Now this whole arrangement will occur how many times? Let's count that as well. I'm going to make you relive the concept. When the C is here, once, twice here, thrice here, and the 4th time here. So this whole arrangement will occur four times, right? Now, if a better example would be that as this C was moving here, this C was also taking this place, while this distance of 3 letters was being maintained, right? A C here, a C here. Then this other case was this C moving here and this C going there, still 3 in between, right? And we counted this as well. How many is that? 1, 2, 3, 4. 4 cases of the same arrangement. So instead of going for plus 6 factorial divided by 2 factorial, simply just multiply by 4. Shortcut is 1 as this, 2, 3, 4. Just multiply by 4. Simple as that. And you get your answer. Does anything repeat? Nothing repeats, right? Yep, we're good. So 6 factorial divided by 2 factorial into 4. Into 4. 1440 is your answer. 1440 ways of arrangement. Hi, is this the final part? This is the final part. Damn, this went by quick. This is all easy. Scene. 5 letters to be selected out of the 10. So we already know it's a combination question in the word Casablanca. But see, find the number of different selections in which 5 letters include at least 2 A's, at most 1 C. Okay. So greater than equal to 1A and less than equal to no, at least 2 A's, sorry, greater than equal to 2 A's and at most 1 C, so less than equal to 1 C. This is the condition, this is the condition. 5, so let's make cases. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Moving on. 1, 2, 3, 4, 5. Let's think about it. Okay, so how many A's? We have 4 A's and we need to go into at least, and we are going for at most 1C. That means 0C, 1C, and 2C's. No, no, no. At most, what does at most mean? 1 or less than 1, right? So 0 or 1. It could be 0C's and it could be 1C, but not more than that. Got it. Huh. So, my friends, let's just put 2 A's, 0C's, 2 A's, 1C. That's it. Let's increase the A's. 3 A's, 0C. Make one more. I need to remain to my color code. 1, 2, 3, 4, 5. This is gonna be a lot actually, damn. Okay, 1, 2, 3, 4, 5. There we go. So 3 A's and 0C. No, 1C. At most, yep. Now 4 A's, 0C's, and the final case will be 1, 2, 3, 4, 5. Did I do that right? Yep, I did. So 1, 2, 3, 4 A's and 1C. Now this is just one whole selection, right? Because it's gonna be what? All of the positions have been filled, one into one into one into one into one, right? Everything is fixed because we are looking for different selections. So that's just gonna be one way. Keep that in mind. And that is all. Is that all? That is all. Okay. Let's do the calculation. So remove now, as we were dealing with A's and C's. Now, if when it talks about different selections, I have mentioned many times before, if it talks about different selections, anything that repeats must be considered by you, and usually they are very kind enough to give you a condition that decreases your cases. So even though there is no C being considered here, we will forget about it because we're manually configuring the position or consideration of the placement of the A's and C's, that the letters that are repeating, right? So forget about them. C's and A's, forget about them. There we go. All of them. Now the remaining are 1, 2, 3, 4. 4 remaining to be selected. Are you sure is that 4? 1, 2, 3, 4. Yep. ये गलती मैं कर चुका हूँ, by the way. Exam में I remember in my mocks or midterms, I would like count that wrong. I would be like, I'll blindly in a hurry go. Instead of 4, I'll go for 5. So don't make that mistake. We're selecting from the remaining non-repeating letters, which are 4. Out of these 4, 3 can occupy these 3 positions, plus only 2 here, plus only 2 here, plus only 1 here. Plus only 1 here as well, plus the final case, and your answer is, let's get you the answer. Okay, 4C3 plus 4C2 plus 4C2 plus 4C1 plus 4C1 plus 1. 25. Good answer. Acha, something to give yourself a little peace of mind is your answer usually should look like this. If it's in multiples of 5, when it's a possible selection question, if it is in multiples of 5, you already know you're right. Now this doesn't go always, but it's mostly. Just even look at the questions we've done. 35, 65, 30. Those were our answers, right? So mostly this is your sign that you've done it right. Making sure you considered all the cases, right? There could be a coincidence. Don't come to me then. Huh. And that, my friends, is all the summer variants. Congratulations. Pat yourself on the back if you understood and made it through all those. I hope I was able to help out. Let's move on to the winter variants down below. Okay, now we begin with the 2023 weather changes to winter and paper 5-1. Here we go. Question 6. दो टेबल है डायग्राम दी हुई है इस बार टेबल एक्स एंड टेबल वाई इन अ रेस्टोरेंट द टेबल्स आर रेक्टेंगुलर ओके शेप बता रहे हैं पता नहीं क्यों ईच टेबल सीट्स 4 people 1 2 3 4 1 2 3 4 okay two along each of the longer sides there we go 8 friends have booked 2 tables x and y okay Rajat Sue Tan are 3 of these friends so distinction banani 8 friends in total out of them, we have Rajat, we have Sue, and we have Tan, right? And the remaining, how many? 3 of these. No, no. 8 minus 3 is 5. Remaining are 5 friends. These are normal people. Now, party. The 8 friends will be divided. I already know, I just need to select into 2 groups of 4. One group for table X and one group for table Y. Simple. Find the number of ways in which this can be done if Rajat and Sue must sit at the same table as each other and Tan must sit at the other table. Okay, not so difficult. First case is gonna be when table X consists of Rajat and Sue on one side. Rajat and Sue, that is your table. And I do not need to consider they are seated on this side as well because it's just selection. And table Y consists of tan, Rajat and no, tan, only tan over here, tan, right? And the remaining seat, there's your table, there's the other seats, and I'll add a 2 factorial. Why would I add a 2 factorial? This 2 factorial will decide. Actually, wait, let me do the whole thing. Wait. Another case, let's make another case. Another case would be tan sits on table X and Rajan and Sue seat on table Y. But instead of adding another case, I can simply say, I can do this, that these two move here and this whole gang or this person tan moves here. So that is just going to be 2 factorial, right? They're going to move from table to table. So that is one thing to keep in mind. Now moving on to their selections. Actually, no, that would mess up our combination concept. This is a shortcut, right? This is a shortcut. Now, this is just a shortcut. Let's leave it at the shortcut thing. But let's remain true to our concepts. And that way, there will be a lesser chance of error, right? So that is the main goal. Let's do that. Let's not go to shortcuts. If said combination, we stick to combination. We do not occupy or employ easier methods. So we make two cases. The other case will be X contains tan and your table Y consists of Rajat and Sue. Actually, I could have just did times two. Times two would have been nice because it's going to be the same selection. If I'm no, actually, wait, the selection might change as well. Let's do the selection. And do not occupy shortcuts, please. I was just thinking. This is my thought process, right? Thought process is the point. Now, let's start selecting. So, Rajan and Sue are fixed that they're going to be represented by 1 and 1 on that table. And for those two seats selected, done. What about these two seats? Out of the 5 friends, 2 of them are seated here. Table X complete. Moving on to table Y. Table Y has Tan fixed. Tan sitting there chilling, already selected. Then we have the remaining 3 people. Now, how many people did we have remaining? We have 3 people remaining because two of them are seated on table X. Select them, 3 seats remaining, filled. That is one case. This is whole one complete case. Moving on to the second case. See, the selection did change. So if I occupied factorial there just to think of a shortcut, that would have messed up my answer. So please be careful. Whenever it says divided, whenever you know it's a combination question, you do not think about factorial. Got it? Now, moving on. Right. Now, one, two, three. 3 seats remaining on table X because tan is fixed. So tan is fixed. 3 seats remaining. So 5C3. Then we have Rajan and Sue fixed over here. On any side of the table, we just have to give context that they were selected for two of the 4 of these seats. Now 1 into 1, 5C3, and the remaining 2 people, because 3 have been seated here, can be seated on these 2 seats. And that is your whole selection. I hope that made sense. Let's get you the answer. Actually, wait. It's only on the same table. Okay, good enough. Good enough. There could be a difficult question. Let me give you, actually, let's get the answer for this. Then I'll help you think of a different way this question could be tested. 5C2 plus 5C3. 20 is your answer. There we go. So 20 ways this selection can be made. 20 ways. Now that's out of the way, let's think about what if the question said find the number of ways in which this can be done if Rajan and Sue must sit at the same table on the same side as each other. The same side would mean this selection, that Rajan and Sue are on the same side. But in this question specifically, it mentions that they're seated on the same table, right? So they could be like the arrangement I've shown here, or it could have been something like Rajat here, Sue there, or Sue here, Rajat there. It could be any because I've simply just said 5C2, right? 5C2. Actually, I've simply I've simply said 5C2. That means that the remaining two people out of the five could just occupy any of these seats, while these two are fixed on any two of these seats, and the remaining two seats that will be left will be occupied by these two, right? So Rajan and Su could be here, they could be here and here. This one into one just represents that, right? But we need not worry about where they are seated, right? This could be anything because it's a selection question. We do not worry about arrangement, right? So do not get into that. But if it said that they were seated on the same side, actually, would that have changed the question? That is the question. If it said they are seated at the same table as each other and on the same side, then what would have changed? I don't think anything would have changed. No, nothing would have changed, right? Because then that would have been our context to the question that they are seated on those sides. Yeah, the selection wouldn't have changed. Why? Because see, the selection or combination does not care about arrangement. Even though the question wants you to have them arranged a specific way, then what then the meaning behind the numbers would change. See, here this one represents that Rajat has occupied one of the four seats, and this one has the meaning that Sue has occupied one of these four seats, and the remaining two seats will be occupied by these two people. That is the meaning I have given these words, these letters, right? But if it said they were seated on the same table on the same side, then I would have said, okay, Rajat here, Sue here, or arrange it this way: Rajat here, Sue here. You do not need to care about which side, right? Just one side. That's the context. Then this one would have only referred to Rajat or Sue on one side. Actually, give me an Adhan break, please. Okay, so we are back, but not so early. I was recording that part in a midday basically, and now it's night. So that break lasted too long, but where were we? Where we were at talking about how even if it's a selection question and it changes the word and asks for something in the sense of arrangement, right? Like it was same table on the same side, right? But and they say that's an arrangement, a certain arrangement they want, right? But we already know that they want us to divide, right? So it's something, some selection we need to show. Only the selection we need to show, right? So we're gonna forget about that, and this one therefore could mean this certain arrangement that would have satisfied their question. And in this case, the ones have a different meaning. The 5C2 has a different meaning. Just like in physics, we say that physics has given the words and letters in maths meaning, right? That's something physics teachers usually flex to the mathematicians, I'm sure. But yeah, that was the concept I wanted you to think about. Moving on. So yeah, just regardless of arrangement or a condition, if it's a selection question, you simply need to show the selection of that specific arrangement, just context of that arrangement, right? Moving on. Ah, la, 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 here we go. Now, when the friends arrive at the restaurant, Rajan and Sue now decide to sit at table X on the same side. Okay, so Rajan and Sue want to sit on table X. Let's make it X, Rajat and Sue on the same side as each other. Okay, so there are two sides, this above and below. I'm positioning them here for now. This is your second side as each other met. Now, the second condition goes, Tan decides that he does not mind at which table he sits. Okay, so let's forget about Tan, right? Now the distinction has changed. How many? Eight friends. Okay, so eight friends. Now Tan has no problem. There's no condition on Tan. So Rajat and Sue are the distinct people, while Tan is now part of the remaining six friends. Okay, makes sense. Now, okay, find the number of different seating arrangements for the eight friends. No sign of anything else. We are arranging all of them. So this is a factorial question. Got it? This is your table Y. This is that, and this is the other side. Now this is a very tricky question. Now, because see, now we need to arrange people after selecting them. on each table, right? Huh, because there is a division of tables, that means there is some selection as well, and there is arrangement, so very complex. Let's think about it. Okay, so Rajat and Sue will occupy these positions. Let's fix them. One for Rajat, one for Sue. They are on the same side at the moment, right? Now, for the remaining, how many remaining people do we have? We have six remaining people. So six remaining people. Out of them, two can occupy these positions. I'm gonna mark it with pink. One guy here, one guy here, right? So that is gonna be out of the six, two people selected for this table, and the remaining one, two, three, four, remaining four can go over there. 4C4. Makes sense, right? Now the thing is, one thing I'm going to add over here is 6C2 into 2 factorial. Why? Because these two people can sit here and they can move about their own positions, right? And give you a different arrangement each time. Now let's talk about Rajan and Sue. They are on the same side, but they can also move about their own seats. So Rajat can come here, Sue can go there, and that is a different arrangement each time as well. So I'm going to add a 2 factorial here as well with these ones. So I know that one was for Rajat and Sue. This 2 factorial was for these two people. Now on table Y, anyone selected out of these four people selected for table Y, all of them can move about their own positions, right? All four seats, 4 factorial. Now there's a question, sir, why 4 factorial here and why were you like 2 factorial over here and 2 factorial over here? Well, it's a simple thing. See, look at it this way. If I do a 4 factorial here, all these four people will rearrange them. Whoever, let me change colors, wait. Okay, there we go. Whoever was seated here will move here. Whoever was seated here can move here. This guy can move there. This gal can move there. I do not know, right? It's random. But on this table, it's not random. It cannot be random. Why? Because there is a condition that these two folk have to be together. So I'm gonna think more specifically. I hope I was able to get that to you. Now, so we've arranged these four, we have arranged these two, we have arranged these two. Now, our arguments who have to be on this table, so there will be no table change for these two, right? So I'm going to remove that from there. Now, they've said that they have to be on the same side, correct? This whole group can also move to this side, and this whole group will have to be forced to be moved over there, right? So this whole chunk of box and this whole chunk of box can move about this whole object, and this whole object of two people can move about their own positions, right? And how many are moving? Two. So that is also going to be a 2 factorial addition right there, right? So let's that should be all, I think. I am pretty sure that is all. We have met the condition. Rather than Sue on the same place, they can move about their own seats. The two people selected for these two seats can move about their own positions to give a different arrangement. The sides can change each time, so that's a 2 factorial, right? Because Rajat and Sue can be together on this side as well, right? Now, everything on this table is done. Moving to this table, four people left, four people seated, and they can move about their own position. So that's a 4 factorial. No condition on this table. Nothing. We cannot change tables, right? So that nothing, y has nothing to do with x. Now you might think, sir, just a query, very pointless but important. Now, it could be, sir, what about who, I don't know who four people are seated here. Maybe we are talking about a specific case. No, my brother or sister, we are not. See, it's 6C2. Combinations does this. Combination, the point of combination and permutation is that any out of the six, any two, out of the four, any, and out of the two people placed there, the remaining any four people will be seated on the next table. So that will consider all the combinations with their specific arrangements. And that covers everything. Let's check out the answer. I am pretty sure I have covered everything, haven't I? Yeah, I have. I'm pretty sure I have. 6C2 into 2 factorial. Then another 2 factorial for Rajan and Sue. The two ones for them being fixed. 4C4 into 4 factorial into 2 factorial for the table change. Oh, not the table change, the side change, right? And the answer you get is 2880 ways of arrangement. I hope that was clear. This is a genuine good question. A question like this was last tested in 2011. I am remembering in my days when I was practicing like a crazy person. So yeah, it's not that complex, but it's something to think about, definitely. I'm gonna make sure I try to find that question as well, the difficult one back in 2011, and do that as well. I'll make a short out of it. Help the viewers. Moving on, part C. As they leave the restaurant, the eight friends stand in a line for a photograph. Okay. Now all eight are being arranged in a line. Factorial question. Find the number of different arrangement if Rajat and Sue stand next to each other, but neither is at an end of the line. Okay. Easy question. So one guy has to be here, but but actually let's make a distinction. There a condition on Rajan and Sue, eight friends, out of them Rajan and Sue, and then we have the remaining six people. Okay, now on the ends, I do not know who will arrange themselves, right? So out of the six people, any two, right? There is no specific persons. I can say any two can occupy these positions at the end, and the remaining actually how many remaining? Eight minus two is six. So one, two, three, four, five, six. There we go. These six and these two ends, seven, eight, can have any two people, but they must not be Rajat or Sue. So I'm gonna go okay. Now see, here comes the context part. Out of sorry, out of the six people I have, which do not have Rajat and Sue part of it, any two, please come and stand on the ends, these two ends, right? So that's, and like for example, if Tan is here and another uh, Farida is here, these guys and gal can move about their own position as well to give you a different arrangement. Tan could be there, Farida could be here. So there is going to be any two people selected from the six can occupy those positions and move about those positions to give you a different arrangement each time. And the context, the meaning I've given it is that the two people are on the ends of the line. That is the meaning I've given it, right? Now the ends condition have been met. Rajit and Sue will never be at the end in any case. Moving on to the centerpieces. Now, in these centerpieces, as this condition of the ends is being met, I have Rajat and Sue have to be next to each other. Got it? Change colors. Rajat and Sue have to be next to each other. Anything you need together, you box that up. There we go. Now, and Rajat and Sue inside the box. Now let's do it inside the box. We can first go for 2 factorial, no repetition, and then outside the box I have one object, two object, three, four, five. Five objects, that's gonna be 5 factorial. Is that all, my friends? That is all. Easy question. So we have 6c2 into 2 factorial into 2 factorial into 5. That, my friends, is 7200 ways. So now you have to get yourself used to the integration of combination and factorial together. Whenever there's a division like this, a certain random condition or a random position that you need to select for, or here for example we had tables to set divide in without the mention of divide because they had to show that it was a factorial question. You have to only mess with the arrangement, but in that arrangement there's a division of tables. That means there is some essence of combination. So that's how they can play. Very good question, very difficult one as well. I hope it was clear. Moving on to variant 2. Let's get this over with faster. Okay, so question 7. Find the number of different arrangements of the 9 letters in the word Andromeda. This is your word in which no consonant is next to another consonant. That means we need to employ the universal separation method to separate things. Whatever we need to separate, we forget about it. So D, M, and R are our consonants. So D, M, N, R. Any repetition of the D, M, and R, another D over here. A, O, E, A. That is something that is not in consonant, that's a vowel. Vowel, whatever, how, I don't know how you pronounce it. So A, how many A's? We have two A's. A, O, E. Now, how do we go for universal separation method? We forget about whatever we need to separate, forgotten about the consonants, right? They had to be separated. And no consonant is next to another consonant, that means they are never together. That means universal separation. How do we do universal separation? I'm giving you the whole thought process. How do we do, how do we do universal separation? We forget about the thing that we need to separate. Arrange whatever remains. So A, O, E is the remaining. I've arranged them. 1, 2, 3, 4. That's gonna be 4 factorial. Anything repeats, yep. 2 A's repeat twice, 2 factorial. Divide that, and I've counted it right. I'm asking myself the questions I made errors in before. Make sure you do that as well. 4 factorial divided by 2 factorial. Then we unlock positions. How do we unlock positions? We think about the first, everything in between. and the last position. Count them: 1, 2, 3, 4, 5. We have unlocked 5 positions, and how many will be occupied? 1, 2, 3, 4. 2 Ds are also part of it, right? So 2 Ds, 1 M. Actually, let's count here: 1, 2, 3, 4, 5. So okay, all 5. Great. All 5 will be filled, and they can move about each position. For example, D here, M here, N there, R there. That's all 5. They can all move about their own position. This is only one case I'm considering, right? Now that's going to be 5 factorial, and D repeats twice, so divide that as well. And that, my friends, is your answer. Is that okay? I hope so. 4 factorial divided by 2 factorial and 4 factorial divided by 2 factorial into 5 factorial divided by 2 factorial. That gives you 720 ways of arrangement. Simple question, moving on. Part B. I am teaching myself not to use easy a lot because I think I'll have to start a counter for how many times I say that. I hope not. That is hard to edit. Part B. Find the number of different arrangements, factorial question, of the 9 letters in the word Andromeda, in which there is an A at each end and the D's are not together. Another universal separation question with another condition. A's have to be at each end. Put them there, one here, one here. Fix them because we do not have to count the probability of this. So it doesn't matter that this A occupies the first position as well, because we need to give different arrangements, right? So it doesn't matter which A is where. Because they will repeat themselves. That's going to be 2 factorial divided by 2 factorial. And we do not want that repetition. We only include that repetition when we're talking about probability or most probable arrangements. Anyways, of the 9 letters in the word Andromeda, 9. So 9 minus 2 is 7. So 1, 2, 3, 4, 5, 6, 7. Now, the D's are to be separated. Forget about the A's and those positions. They are fixed in their positions, right? Now, in the remaining 7 positions, 1, 2, 3, 4, 5, 6, 7, 7 positions, we need to separate the D's. Now, keep in mind, 2 of these will be occupied by the D's, right? And whatever do we need to separate, we forget about. So please remove those 2 positions for the D's. Remove the 2 positions. We have arranged the remaining on these positions. 7 minus 2 is 5. The remaining 5 have arranged themselves here. Let's arrange them actually. Any 5 letters that will be placed here. Go for 1, 2, 3, 4, 5. 5. That's going to be 5 factorial. Now unlock the positions. How do we unlock position? We think about the first one, everything in between, and the last one. So how many did we unlock? We unlocked 1, 2, 3, 4, 5, 6. We unlocked 6. Out of that, how many will be covered? 2 will be covered, and a 2 factorial for them to move around. But keep in mind, these are D's. They cannot move about their own position without repeating themselves, and we're talking about different arrangements. So that's going to be a divided by 2 factorial as well. Anything repeats in this 5 factorial, let's make sure here as well. When we are doing this 5 factorial, we have placed the A's and we have placed the D's. N, R, O, M, E. All different, nothing to divide here. So that's your answer. See, it's a game of thought process and learning to employ these techniques. Okay, 5 factorial into 62, 1800 is a good answer. 1800 ways. So I know I'm on the right track. Moving to part C. Okay. 4 letters to be selected at random. Combination question from the 9 in the word Andromeda. Find the probability. 2023 में probability और selection का मतलब होता है possible selections. Find the probability that this selection contains at least one D and exactly one A. So A's and D's have a condition on them. Whenever it's a possible selection question, please do the boxing thing. Anything that is a condition on them, box that up. A's and D's have a condition. So box the A's, 2 A's, and box the D's, 2 D's. Anything else will be put in your final box, which is your big box of non-repeating letters, and sometimes repeating letters are part of it as well. Okay, so how many remaining A's and D's gone? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, 5. So N, R, O, M, E are in this box. Nerome. Now, 4 letters are selected, so let's start making the cases now. This was the first step of possible selections, right? Now let's start making the cases. 1, 2, 3, 4. 1, 2, 3, 4. Okay, 1, 2, 3, 4. And let's start thinking about him. So first case, at least 1D, that means greater than or equal to 1D and exactly 1A. So every case must have an A. And at least 1D would mean 1D has to be part of it always. So 1 or greater, right? So 1 is being considered here, greater is being considered here. I cannot go for 0. So there will be no further cases, 2 cases only. I'm afraid that's an easy answer. Okay, so that will be now this A. Where is this A coming from? This A is coming from any one of these two. So it was possible that any one of maybe this A occupied that position, maybe maybe that A occupied that position, right? So I'm gonna go select from this box. 2C1, 1A was selected out of the D's, 1D was selected, and out of the remaining box, the final no condition box is 1, 2, 3, 4, 5. Out of the 5, the remaining two positions will be occupied. Final one, 2C1 for the A, 2C2 for the D's, and 5C1 for the remaining non-condition box. Means that these these letters that do not have any condition on them. Got it? Alphabets, basically. And that is your favorable condition. You keep in mind, you need to give a probability. So, right, this is you finding the numerator, the favorable conditions. Answer of the favorable conditions in the denominator, you will be giving all the outcomes without any consideration. That's going to be 9C4. Out of the 9, any 4 position or the 4 positions filled, right? That's all your outcomes. And in the numerator, you have favorable conditions. So 2C1 into 2C1 into 5C2 plus 2C1 into 2C2 into 5C1. I hope I'm right. 50 divided by 9C4. That sounds about right. 50 over 9C4. Answer divided by 9C4. Okay, so the answer is 25 over 63. 25 over 63. I hope we are right. Answer. I do hope you are right. Is there something I'm missing? AD, at least 1D, that's one case. Increasing the D by 1, and then we are out of D's to increase. We cannot decrease anything. Yeah, that's gonna be all. And the calculation is right. 2C1 into 2C1 into 5C2. Yeah, that's right. Okay, so that is your variant 2 question. Good progress, good progress. That was done way faster. Final question, variant 3. By the way, how many marks? 3, 3, and 4. So 6 plus 4, 10. 10 marks for that. Such an important part of your paper, right? So make sure you have enough command on that. Final part, variant 3. Please read the question while I hydrate myself. Okay, party people. Jay and his wife Kaz are having a party. Jay invited 5 friends and each friend will bring his wife. ठीक है? At the beginning of the party, the 12 people will stand in a line for a photograph. How many different arrangements are there of the 12 people? Matlab, factorial question. Identify yourself. If Jay stands next to Kaz and each friend stands next to his own wife. How easy is this question here? Come on. फ्री के 3 नंबर है. आओ करते हैं देखो. जे और कैश को साथ खड़ा होना लाजमी है. These two positions. Actually, first make 12 positions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? 12 made positions made. Now each friend will stand with their own wives. So friend wife, friend wife, friend wife, friend wife, friend wife. You know how husbands and wife forward each other, so FW forward each other. That's lame, I know. I'm the king of lame jokes, apparently, as my friends like to hear it. Anyways, J and Kaz are together, next to each other, so let's box them up. And each friend next to his own wife, so box them up as well. Box, 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 box. That is 6 boxes. Now, first we deal with inside the box. Each box will go over 2 factorial. And instead of writing 2 factorial, actually, no, 2 factorial, once, twice, thrice, 1, 2, 3, 4, 5, 6. 6 times. So 1, 2, 3, 4, 5, and 6. Or I could have just done this 2 factorial to the power of 6, right? Because multiplication shortens to the power of. Anyways, continuing here, I'm going to do it two ways. Now, outside the box, I have one, two, three, four, five, six. Six objects that will move about their own position to give you a different outcome, while the condition of these two people, these two people, these two people, these two people, dot 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 is being met. So these are your arrangements. 2 factorial to the power 6 into 6 factorial. Is that it? Yeah, that is it. 4,680 bits of arrangement. कितना आसान क्वेश्चन था. Moving on, part 2. How many different arrangements are there of the 12 people? If factorial question already, if J and Kaz occupy the two middle positions in the line, okay, so the fifth and sixth, I guess. Yeah, I guess, I don't know. I'll visualize it. Occupy the two positions in the line with J's five friends on one side and the five wives on the friends huh, of the friends on the other side. Okay, ठीक है, ठीक है, ठीक है. So J and Kaz are to be in the center. Five friends on this side, one, two, three, four, five, and five wives on that side. So one, two, three, four, five. Sixth and seventh position occupied by these. These both have to occupy the middle position. So I'm gonna, for my own ease, box them up because they will not move. So inside the box, I'm gonna have a 2 factorial just under them. Now, for these men and women, now interesting occupy on five friends have to be on one side and the wives have to be on the other. There is no mention of which side they have to be on. So I am gonna do one thing. I'm gonna do this. I'm gonna make a box of the friends on this side, all five friends together, and all five wives together. Right? Now box that up. Now think about it. This box is fixed, so not moving. Inside the woman, the wives, they all those wives can move about their own position to give a different arrangement. No condition on them. So one, two, three, four, five, and all these friends can move about their own position as well. That's 5 factorial for inside those boxes. And ultimately, these two boxes can move around these two sides. So that is going to be a 2 factorial. And that is your answer. So 5 factorial taken twice into 2 factorial into 2 factorial. Your answer is 557,600 bits. I hope that is right. I think I've considered everything. The side thing is considered, the friends moving, the wives moving, J and Kaz moving while they are in the center. Yeah, that works. I guess this is the last part. Wow. Almost done, people, almost done. And then you can move on to 2024. Part B. For a competition during the party, the 12 people are divided at random groups of 5, 4 and 3. ठीक है. तीन ग्रुप्स बनाने हैं, 5, 4 और 3 के. Find the probability that J and Cass are in the same group as each other, or such a lengthy and fazul question. Okay, let's do the breaking. First, let's make your groups. A group of 5. Okay, no. Let's not be lazy. Let's not be lazy. Let's make a proper group. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3. Three groups. 5, 4, 3 of 5, 4, 3. Now J and Cas have to be the same group as each other, and we have to find the probability. Great. Now let's do a thing over here. Let's make a favorable conditions on top, and in the denominator you have your all outcomes. So let's do the all outcomes. All outcomes will be 12C5, right? Out of the 12, any 5 occupy the first group, then the remaining 7 occupy the 4 group, and the remaining 3 are in the final group. That's the all possible outcome. Now the favorable outcomes, let's calculate them. J and Kaz have to be in the same group as each other, while the remaining people do whatever they want. So they can be in this group, right? Are in the same group. They can be in this group in another case, and they can be in this group in the third case. So there are going to be 3 cases. Let's make the 3 cases. 1, 2, 3, 4, 5. Once I got a special life. 6, 7, 8, 9, 10. Then I let it go again. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3. Okay, so then in the second case, they are in the group of 4, and in the third case, they are in the group of 3, right? But they are in the same group. This is the 3 ways it can be done. Yeah. So now this is a selection question, by the way. How do I know? I know because of this keyword, right? So I do not need to worry about the arrangement and any repeating groups because 543, you get what I mean, due to the crocodile dilemma in 2022. Now fixing them there because we need to give, it's a probability question, right? But J and Kaz are people, so I cannot employ them into groups. Even if I want to group them, J is going to be in one group, Kaz is going to be in one group, right? So it's just going to come down to 1C1 and 1C1. 1C1 is 1, right? You can check that in the calculator. So when it talks about people, you can simply fix it, even if it's a possible selection question, because there's nothing repeating. Humans won't repeat, right? Now, oh, yep, no, actually, yes. Now, out of the 12 people, J and Kaz, and the remaining 10 people. Now you will be selecting for the remaining positions out of the 10. I almost made this mistake. Now 10C3 for this, remaining 7 people, because 3 have been put in this group, they will occupy the 4 positions here, and then finally the 3 remaining people here. Second case, out of the 10 people, 5 people occupy these positions. Then out of the remaining 5 people, firstly, let's think about J and Kaz being occupying these positions. Then the remaining 5 people, out of the remaining 5 people, 2 positions in this group are left. They occupy these positions. 3 people remain. 5 minus 2 is 3. 3 people remain. They occupy those positions. Right? Now 10C5 here as well. Moving on. 5C4 here. J and Kaz are fixed. By the way, I made a distinction. If anyone's wondering why this is a 10C5 instead of 12C5, because they had a condition on G and Cas. So I made a big distinction of them over here. And I'm only going to think about the remaining positions through these 10 people, because J and Cas are manually being placed, right? And the remaining one person can occupy this position. 3 cases that will make your favorable outcome. Let's get your favorable outcomes there. So favorable outcomes, 10C3 into 7C4, that's it, plus 10C5 into 5C2 into 3C3, plus 10C5 again, 5C4, and 1C1. So your 5 favorable selections are 7, 9, 8, 0. Let's get you the probability divided by all possible outcomes. 12C5 into 7C4 into 3C3. Okay, 3C3. 19 over 66 is our final answer. And that is all, people. Finally, that took a lot of energy. And we are done, my friends. We are done. Congratulations. Pat yourself on the head back again, because this was a good group of questions. Let's move on to the next video where I will cover the 2024 variants, inshallah.